which I'm calling Permutations Part 2. We're going to be dealing with permutations officially, and we're also going to be dealing with factorial notation officially. You already know what these are. You know what factorial notation is. 3 factorial means 3 times 2 times 1. You already know, although I haven't taught it to you officially, like it's not in your notes, that a permutation is an arrangement of a group of items. But we're going to formally deal with these today. So we're going to be evaluating expressions that have factorial notation, solving problems using a formula for permutations, and solving equations which combine formulas for permutations with factorial notation. So factorial notation, this is obvious. If I say to you, how many ways can I arrange 7 books on a shelf? We're arranging them in an organized way, not piles or different angles, they're in a row. The answer can be found using the fundamental counting principle by saying that the first book you put on the shelf on the left, you have a choice of 7 different books to choose from, then 6, then 5, etc. And I think this is pretty straightforward. I think you get this. But officially now, even though I told you this on Friday, we write that as 7 factorial. It's pronounced 7 factorial. But now we're going to get a little bit of algebra into our system. What n factorial means is you're going to take n and multiply by 1 less than n, and then multiply by 1 less than that, and continue doing that until you eventually get down to 3 times 2 times 1. Now, I understand that you don't need this definition, and in fact, this definition is really not workable if you have something like 3 factorial, because it would be 3 times 3 minus 2, or 3 minus 1, which is 2, and then you hit the point where you have 1 here, so the rest is not necessary. But if I had something like 80 factorial, we would write 80 factorial as 80 times 79 times 78 times 3 times 2 times 1. Okay. If we wanted to write it in expanded form, if we just want to write what it is, you'd write 80 factorial, right? You don't need to expand it out. This writing times 1 at the end is something that you'll first look at and go, I don't really need to do that. I know you don't need to, but I would like you to. Okay. Calculate each of the following. Well, I suppose we could take 5 times 4 times 3 times 2 times 1. That's 20 times 6. I believe that's 120. And for whatever reason, I'm sure I showed you where the factorial function is on your calculator. Did I? Yeah. I mean, I like lots of things from the past, but I like old calculators. There was every scientific calculator had a factorial key right there. You'd just use it. You wouldn't have to go hunting for stuff. But where you will find it in your calculator, and there may be, depending on the model and the operating system, other ways to access it, is you would enter the 5, and then you go to your math menu, and it's under probability. So you can either scroll to the right or scroll to the left to get there. And there it is. I would say to you that, certainly 2 factorial, 3 factorial, probably 4 factorial, maybe 5 factorial are things that you don't need to access all the time. 3 factorial, 6. 4 factorial is 24. Anyway, 5 factorial is 120. 7 factorial, well, I would probably just do this and edit this to include a 7 instead of a 5. It's 5040. And that's just an introduction to make sure you know where you get that factorial function access on your calculator. I want everybody to listen carefully about what I'm asking in B. It turns out that I can figure out what 50 factorial over 49 factorial is without ever using the factorial key and without going 50 times. I don't need to do that. I can figure out that the answer is 2450 very quickly in my calculator. And the question is why? And the answer to this is an important thing for what's coming up. Do you know, Alex?
If you were to break it up into all of its factors, all but 50 times 49 would be canceled, which is...
I like that you said if you were to break it up into all the factors. That's why we call it a factorial, because it's listing all of the factors of the number. What are the factors of 50 factorial? They are 50 times 49 times 48 times, I'll go one more, times dot, 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 times 3 times 2 times 1. And this is over 48 factorial. But here's the key idea. All of the factors in 48 factorial are factors in the 50 factorial. In fact, this, all the way to the end, is 48 factorial. So the smaller factorial is contained as a factor in the larger factorial. And it's always going to be possible to cancel the smaller factorial out of the larger factorial. And presumably, if you take 49 times 50, you get 2450. You can check that out. So this is 49 times 50, or 50 times 49, I don't care, which is 2450. And that's not a problem you would be asked about in Math 30 because there's numbers there. But in order to solve problems that involve equations that are algebraic and they have factorials, we need to understand how to simplify factorials by canceling the smaller factorial out of the bigger factorial. I want you to notice before we move on, it would serve me no purpose to expand the smaller factorial. I'm always expanding the bigger factorial to see what I can cancel, where the smaller factorial is inside of the bigger one. Example 1, simplify. Well, I have one factorial divided by another factorial. The factorial on the bottom is smaller than the factorial on the top. N minus 2 factorial has to be smaller than n factorial because n is a bigger number than n minus 2. So we start expanding the larger factorial. And you can pretty much stop as soon as you see the smaller factorial. I always like to add one more here to make a point. Again, I don't know what n is. N could be 1,000,000. It doesn't matter. I know that this string of factors can be abbreviated this way. Well, maybe abbreviated is the wrong word. Expand it out. Abbreviated, it's just n factorial. But I can expand it out this way. This is over n minus 2 factorial. Don't forget to write the factorial on the bottom there because we didn't expand it. And this thing, all the way to the end, is n minus 2 factorial. So again, we can do some canceling. Cancel the n minus 2 factorial with the n minus 2 factorial. And our answer is n times n minus 1, or n squared minus n. Just looking ahead, why would we do such a thing? Why would we want to do such a thing? Well, for the same reason that if we had an equation with square roots, we would square both sides to get rid of the square roots. Or the same reason if we had fractions in an equation, we'd multiply everything by denominators to get rid of the fractions. If you have an equation that has factorials, you got to get rid of them and turn it into a math 30-1 problem prior to factorial notation. Or better yet, turn it into a grade 11 math problem or a grade 10 math problem where they didn't have factorials. N plus 3 factorial over n factorial. So which is the larger factorial? N plus 3 factorial. N plus 3 is a bigger number than n. So to me it would make sense that the factorial of a bigger number will give you a bigger number. So we're going to expand n plus 3 factorial. But we don't start with n. It's not n times n minus 1. We're starting with n plus 3, and then it's going to be n plus 2, and then it's going to be n plus 1. and then it's going to be n. Now, then it's going to be this. I want to show something to you, but I don't want to do it just yet. Right? So it's n plus 3, then 1 less is n plus 2, 1 less is n plus 1, 1 less is n, then n minus 1. I certainly didn't need to write all of that because I know this is over n factorial. I could have pretty much stopped here and said this is n factorial, so it cancels. Are you with me on this? Okay. So this cancels. And in fact, what I was going to write, we'll write our answer in a second. I was going to write this. And I don't think there's anything wrong with writing it. Notice there's a factorial notation after that n. I'm not saying just times n. That n factorial means the n times n minus 1 all the way down the line. And then these cancel. So our answer is n plus 3 times n plus 2 times n plus 1. And I don't see any reason why we should multiply that out. I think that's fine. But we had a unit on polynomials, right? And you know how to solve polynomial equations. So if I told you that this was equal to some number, and I'm not going to make up a number because it has to be equal to something that is going to make that equation true. Not any value will make it true because n has to be a natural number. Then, on a diploma exam, I might say determine the value of n algebraically, in which case you would have to multiply out those three binomials, subtract the a over, and dig in to the factor theorem and synthetic division to solve it. But these things are always factorable because n is a natural number. So it's not as tough as it would sound. Anyway, that's our answer, what's written in brown at the bottom of the screen. This is interesting because I have a factorial not over a factorial, I just have it over some factors. But let's start expanding the factorial, and how many of you see what will happen? You're kind of, it's like chess, you're one or two moves ahead and you know what's about to happen. If you don't see it, well, I mean, you have to write it down anyway, if it's a written response. Just start expanding the factorial that you have. And right away, I can see on the bottom I have an n and an n minus 1. Those are factors. But n is a factor in n factorial, and so is n minus 1 a factor in n factorial. You know, if it were just me, and I were just working something out, I probably wouldn't write 3 times 2 times 1. But again, I recommend that you do that, particularly on a written response. So what happens this time is it isn't a factorial that cancels, it's just a pair of factors. And you're left with n minus 2 multiplied by n minus 3 all the way down the line, which is n minus 2 factorial. So n minus 2 factorial is the answer. Okay, permutations. I've already told you what a permutation is. A permutation is a group of items that are arranged. So once again, if I have, how many people I have in the room here, let's say 28 students in the room, and I'm going to take 4 of you for ice cream at lunch, that's not a permutation. You know, if I decide to take these 4 gentlemen in this row, I'm just taking them, right? It's just those 4 people. The order doesn't matter. But if I had 4 gift cards, and this is the analogy I usually use, an Earl's gift card, a BP, is Earl's still a thing? It is? An Earl's gift card, a BP gift card, a Coliseum steak and pizza gift card. That was a place in my youth. And a Subway gift card. Those are 4 different things. So if I say I have these 4 gift cards and I'm going to choose 4 people to give them to, and I choose this same group of 4 people, there's an arrangement involved, right? Because if you get the BP gift card, that's different than you getting the Subway gift card. So even though I'm not physically arranging individuals in a line, the order in which I hand out the gift cards matters, and that would be a permutation. So order is important. This is the most important idea. If I'm playing cards, I'm playing poker on Saturday night, the order of cards that are dealt to me in 5-card stud, where I'm dealt 5 cards, doesn't change the outcome of the game. If I'm playing crib and I'm dealt these 4 cards, it doesn't matter the order they were dealt. Those are not permutations. But I hope you would agree that phone numbers are permutations. If I tell you the 7 digits of my phone number and I don't tell you the order, then good luck getting a hold of me. Okay? So determine the number of permutations of all of the letters of each word. This question is only different because it's phrased differently. If you were to answer this question, what we're saying is we're arranging all of the letters of the word Regina. 6 factorial, right? I don't think we need to do this. 6 times 5 times 4 times 3 times 2 times 1. This is where we kind of ended up yesterday and also where we started this lesson. We said if you're arranging n items all at once, the number of ways to do it is that number factorial, which is, I think, 720. I think I've got that. On the other hand, if I'm arranging all of the letters of the word Ashmont, correct me if I'm wrong, but I'm counting 7 letters there. That's 7 factorial, which I think is 5040. Is that right? Okay, 5040. If you want an actual number, this is 720. This is because of the fundamental counting principle, but you have to kind of use a bit of common sense. I've used this analogy before with you. If 7 times 6 is 42, there's a reason for that, and it's that 7 piles of 6 Smarties is totaling 42. I hope 7 times 6 is 42. Yeah. But you don't have to do that over and over again. You do that once or twice as a small child in school, and you learn to memorize things. You learn shortcuts. So I'm repeating something here at the bottom of the page that's just an important idea. If you are arranging all of the items at once, the permutations, the number of permutations will always be n factorial. So now turn the page, and I want to look at what happens if we select fewer items. So what happens if we select fewer items out of the group, but we're still arranging them? They're still permutations. So I'm going to go through some examples so you get my drift here. There's 7 different cookies. They're different cookies. I don't just mean I have 7 chocolate chip cookies and they're slightly different. I mean there's a chocolate chip cookie, a coconut cookie, a Florentine. My brain is not very creative this morning. I have 7 cookies. You could come up with 7 different cookies. And I go into the kitchen. I'm a little child. I go into the kitchen. My mom's baking all these cookies. And I said, Mom, can I have a cookie? Yes. So I push it. Can I have 2 cookies? Yeah. And I finally get to 4, and she says, you can have 4, but don't ask me if you can have 5, because the answer is no. The question is, in how many different ways can I eat 4 of those 7 cookies? So if I eat the chocolate chip, the oatmeal, the coconut, and the Florentine, that's a different order than eating the chocolate chip, the Florentine, the coconut. Nobody remembers the other one? And the oatmeal. Save the oatmeal for last because, oatmeal. They're different. So how do we communicate this? We use this notation. The P stands for a permutation of items. We have 7 items that we're going to arrange, but we're only arranging them in groups of 4. So if you want to, and this, I think you get this, but it's important that you understand how you can wrap your head around this. If you want to wrap your head around how it's arranged, why is it an arrangement? I line the cookies up left to right, and that's the order I'm going to eat them in. There's a physical arrangement. There are 8 empty seats on a bus, and 6 people get on the bus. That's highlighted there because I need to make a correction to my notes, and I think there's a typo there. It says but instead of bus. So this is complicated because if there are 8 empty seats and I have 6 people, I'm not really arranging the seats, am I? It's not like I'm taking some cookies and arranging them. I'm not taking seats and arranging seats. So we'll talk later about how you can wrap your head around this. But this would be 8p6. There are 8 seats that I can use. And those 6 people are going to sit in those 8 seats. But the order in which they sit is important, so we use p. How many 3-letter arrangements can be made using all of the letters from the words Roxy Music? Well, how many letters are there? I think there are 9. And we're going to grab groups of 3 and arrange them so it's 9p3. So this is just an introduction to get you used to the notation. It turns out that there's a formula, and this formula is on your formula sheet. And through use of an example, you're going to understand why the formula works. What this is saying is, I mean, we can go back. Let's do the cookie example. What were there, 7 cookies? So 7, and I was going to eat 4 of them. And the order in which I eat them changes my culinary experience, right? It's different. So this would be 7 factorial over 7 minus 4 factorial, which would be 7 factorial over 3 factorial, which would be 7 times 6 times 5 times 4. Because the 3 factorial is contained in the 7 factorial. I'm not saying this is how you would calculate it. I'm saying that 7 factorial is this. I'm giving you kind of an operational explanation of how that formula works, what it means. But this totally makes sense. Because if I use the fundamental counting principle, cookie 1, cookie 2, cookie 3, cookie 4, how many choices do I have for the first cookie? 7. And then 6, and then 5, and then 4. And I would say that you probably wouldn't use the formula for something this simple. Okay? How many different arrangements are there using the 4 letters from the letters of the word Ashmont? So what this is, well, it's the exact same. I didn't realize it was the same as the cookie problem. But do you agree it is? So we can either write option 1, we can write 7 factorial over 7 minus 4 factorial. By the way, I don't know what that is. That's 28 times 30, which is 840, I think. Is that what it works out to? 840. You could blindly apply the formula. You could use the fundamental counting principle. Any one of the 7 letters in the word can lead off the arrangement, and then any of the 6 remaining, and then 5 and then 4. Of course, that gives you 840. Or I can use my calculator. And I don't know if you noticed, I didn't draw your attention to it, but in the math menu where we find factorial, you see NPR. So the way I have my calculator set up, I would enter the 7. I would go to my math menu and scroll over to probability and choose NPR and then 4. Now, You never need to put brackets around that whole thing. That NPR notation ties the 4 and the 7 together. It locks them together. I'm curious, if you're in a different mode, does it give you subscripts? I don't think it does. It does. Okay. See if my calculator does. So, and again, I don't like this mode for a variety of reasons. But if I do that, what happens when I go over there? Whoops. It's really going to depend on your operating system. Can you hold up your calculator so I can see what you got? Does yours give you the subscripts? Does yours? Okay. So I can't tell what kind of calculator that is exactly from here. If you got a fancy calculator, a newer calculator, it will put little boxes, I'm presuming, there. But otherwise, you just have to deal with it. Anyway, I'm going to get out of this mode. I don't like it. So I would go 7, hit math, go over to probability, hit this, and then 4. We're okay with that? There are some other weird ways you can get to some of these things. I was just seeing if there was an alternate way, but on my calculator there isn't. So you still get 840. All right, just a point to be made now. Take your calculator and calculate 0 factorial, which ought not to make sense. 0 factorial doesn't really make sense in the definition of factorial, but it's equal to 1. The reason for that is we know, and I'll give you an illustration here. We know that if I'm going to arrange 7 books on a shelf, that the number of ways to do so is 7 factorial, correct? But we also know then that based on what I've told you about permutations, we ought to be able to write 7p7, and it should give us 7 factorial, because that's the answer. But when I put that into this formula, I get 7 factorial over 7 minus 7 factorial. I get 7 factorial over 0 factorial. So the only way for that to make sense, and this is just a high school explanation, the only way for it to make sense is to say that 0 factorial is by definition 1. It's something we need to know. Factorials at higher levels are confusing, and I wish I'll look it up. There's a couple of really unique factorials you can find. This is totally off topic, but if you go 0.5 factorial, it might even be this one I'm thinking of, you get this number. You get a number. If you go 0.6 factorial, well, guess what? You don't get a number. I think it's negative 0.5. Whoops. Factorials are more complicated at higher levels. I just don't want to leave you hanging here with that basic definition of factorials. In post-secondary math, you would study factorials in more detail. By the way, these numbers, 0.888, they're related to pi somehow. Okay. I don't remember the exact relationship. All right, let's move on. We're going to do a couple of examples, and then we're done for the day. Then you're going to get lots more practice with solving problems, whether you solve them with the fundamental counting principle or permutations is up to you. In a particular country, we have license plates that consist of 2 letters followed by 4 digits. So there's no mention of restrictions here. There's no mention that the letters have to be different. So we would assume there are no restrictions. The letters can be any letters. And what that means, it does say 2 different. My mistake. It does say 2 different letters. Can't use the same letter. So if you use the fundamental counting principle, you need 2 letters followed by 4 digits. 1, 2, 3, 4. Listen, you need to choose 1 letter and another letter. You need to choose 1 digit and a second digit and a third and a fourth. And you need to do the numbers and the digits. This is just one long string of Bobby Bear's decisions. He's in charge of the license plate factory. So this would be 26 times 25, and then this would be 10 times 9 times 8 times 7. And I guess we should get a number here for an answer. But I'm not too interested in what the exact number is. It's going to be in the millions, it looks like. Well, that can't be. $3,276,000 is what I get. All right. So there are 3,276,000 different plates that can be constructed. Now, how would you do this with permutations? I would suggest to you that you might not want to do it with permutations, but you might want to. It depends on the individual. Permutations is pretty slick because what you need to do is you need to, out of the 26 letters, arrange them in groups of 2. It's not 7 cookies and you're eating 4. It's 26 letters and you're arranging 2. And out of the 10 digits, you are arranging 4. And that's the answer. In fact, a question on an exam might not ask you to find the actual numerical value. It just might be choice A, 26 choose 2 times 10, 26P2 times 10P4. But let's run it through the calculator. I misspoke because if I say choose, that P is not a P, it's a C. Something different. It's taking the people for ice cream without regard to order. I wish there was a quick way to access this. If you ever find a way, let me know. Whoops. I also think the programming in terms of the screen and what appears here is sloppy. 26P2 times 10P4. I don't like those gaping spaces between the digits and the function. Because when you look at this, the 2 and the 10 are right next to each other. It doesn't mean it's going to multiply 2 by 10. It is going to, your calculator is going to take this and multiply by that. Okay? And you're going to get the same answer. Any questions with 4? Okay, solve this equation, and this is the final example. We want to solve this algebraically. So you need to know how to solve these. Well, what are we going to do? Let's take this np3 and write it as n factorial over n minus 3 factorial. That's really one of the only things you can do. I'm using this formula and although we could take that 2n times the n plus 8 and multiply it out right now, I'm not going to because we don't have a reason to yet. So what have I done? I've gotten rid of the NPR notation, but I've replaced it with factorial notation, which I need to get rid of the factorial. If the factorials weren't there, I could solve this equation, because then it's just straight algebra. Well, I recognize that n minus 3 factorial is contained in n factorial. if I expand this out, it's n times n minus 1 times n minus 2 times n minus 3 all the way down the line times 3 times 2 times 1. And that's n minus 3 factorial. And this is equal to 2n times n minus 8. So the n minus 3 factorials cancel. And you're left with n times n minus 1 times n minus 2 equals 2n times n minus 8. What we recognize that, yeah.
N plus 8, not n minus 8.
Is it n plus 8? Thank you. Thank you, Craig. What we recognize at this point is if we were to expand it out, it's a cubic function, which means it's polynomial, and the only way to solve a polynomial function is to expand it all out so you can zero it, so you can factor it. And the rule in Math 30 is this. Out of permutations and combinations come polynomial equations. Degree 3 is the highest degree that you would be expected to solve in combination with this stuff. So we're going to expand all this out. I would expand these two binomials first. N squared minus 3n plus 2. We can expand this out as well. 2n squared plus 16n. Now we can multiply this through. N cubed minus 3n squared plus 2n. Might as well subtract this stuff over. We need to zero the equation to solve it. So what do we get here? I have an n cubed. I guess it's minus 5n squared and minus 14n. Can you just double check my arithmetic? I was thinking of something else for a moment there. That looks okay? So I can factor the n out. We caught a break here, and this happens quite often with these types of problems, that there's no constant term. It doesn't always work. But if there's no constant term, then when you factor that out, that's a huge improvement in what we're going to need to do here, because it's quadratic. So I have a factor of n. I have a factor of n minus 7 and n plus 2. I'm presuming you can factor n squared minus 5n minus 14. Two numbers that multiply to give negative 14, add to give negative 5. So I have three solutions here. N is equal to 0, n is equal to 7, n is equal to negative 2. But there is a domain for n. And since this equation had np3, n must be greater than or equal to 3. N cannot be less than 3, because then what you're saying, logically speaking, is you have, one item, and you're going to arrange that one item in groups of 3. I want to point something out to you. Well, I'll get to that in a second. So our answer is going to be this. This is not in the domain of allowable n's, and this is not in the domain of allowable n's. Two things I want to point out to you. It may very well be that if you solve this in some other way on your calculator, you are allowed to use numbers that are less than 3. But we're not at this level, okay? I also want to point out, and I don't know if anybody saw this, I purposefully didn't do it because you're not allowed to. At this point here, some of you might have been tempted to divide both sides by n. And we've talked about this before with polynomials. You're not supposed to do that. Even though in this case it's not going to matter, you never want to divide by factors that have variables in them. They are part of the equation. And I guess finally, well, does anybody have any questions on the work we did to get to the answer? Finally, I don't see these very often, if at all anymore, on numerical response questions. Multiple choice would never be given this, because you'd just put each choice in for n. But you could do this. For y1, you could put xp3. By the way, you can't graph it. It doesn't graph anything. But for y2, I can put 2x bracket x plus 8. I can set my table to start at 3 and go up by 1, because it has to be 3 or more. And then I can go to my table and I can look to see where these things are equal. And they are equal there. Right? Very simple approach. On the other hand, if we scroll in the other direction, they're equal there too. But that's not a meaningful solution, not in this course. The reason is, if you have 0 items, how many ways can you arrange them in groups of 3? 0. Right? You just don't do it. And the right-hand side happens to be equal to 0 there as well. Anyway, that's the lesson. The formal teaching now of what a permutation is in terms of that formula, NPR equals n factorial over n minus r factorial. And then using your knowledge that smaller factorials are factors of larger factorials to cancel, to whittle down factorials in equations. On page 10, 1 to 13, many of these questions are questions you could have done with the fundamental counting principle, and you can still do with the fundamental counting principle. It doesn't matter. You don't have to do these in any particular way. So get started on that, please. I will come around and help you out.